So in this video, what we're going to do is give some of the preliminary kind of definitions and lemma for the Mostowski collapsing theorem, or to talk about what the Mostowski collapse is. And probably we'll prove that the theorem in the next video, but I think it's good to think about the intuition. Seeing it for the first time is a little bit strange, at least it was for me. But what's the point of everything? The point of all of this is that, well, what we want to show is that if we have a well ordering, we want to show that it's actually in some sense the same thing as an ordinal. So in other words, what do we mean by is the same? We mean, well, there's an order isomorphism between a well ordering. If you take a well ordering, there's an order isomorphism between that well ordering and the ordinal. And further, what we can show is that not only is this well ordering isomorphic to an ordinal, the ordinal that it's isomorphic to is unique, and there's only one way to define that order isomorphism. So not only is it like our well orderings kind of classified by the ordinals, it's done in a unique way, which is kind of interesting. Okay, so but what's the definition for us? The kind of what we mean by the same is that there's an order isomorphism between kind of two different kind of orderings. And so what's the definition? An order isomorphism is a function between two orderings. Maybe it's A less than and B less than. We're kind of abusing notation a little bit by using the same ordering symbol. And, if you want to, you can think about them as well orderings, but you can define it for any like partially ordered set, say. And well, what is it? It's a bijection. So bijection, recall, means that it's one-to-one and onto. One-to-one means that distinct elements in A map to distinct elements of B, and then onto means that everything in B is mapped to by something in A. And well, such that this property holds. So what is this saying? This is preserving order theoretic. Like, what we want to do is preserve the order relation. So we're preserving the order relation. And this is a pretty powerful statement because what it implies is that, well, one way to think about what an order isomorphism is that these two orderings, A and B, are the same ordering. It's just we've kind of labeled the terms differently. So A and B are the same ordering. With different labels. And another way to think about this is, well, A and B are kind of one of the consequences of this is that if you have some kind of order theoretic statement, well, it's true in A exactly when it's true in B. So another way of expressing this is that A and B are going to have the same order theoretic properties. So A and B have the same order theoretic properties. Theoretic properties. Okay. All right. So this is going to be kind of the when we say the same, what we mean is something like this. Okay. So we're going to use more of a technical lemma that'll kind of come up in the proof of this result involving the Mostowski collapse. So what is this lemma? Is, well, what are the big orderings that we've been thinking about in the last kind of good chunk of videos? Well, they're ordinals, right? Ordinals are well orderings. And well, one of the results that I think is really interesting is, well, if you have a order isomorphism between two ordinals, so this is an order isomorphism, where alpha and beta are both ordinals. So where alpha and beta are both ordinals. Well, actually, the what we can conclude from this is not only are alpha and beta the same, but F is the identity map. So then alpha is equal to beta, and F is equal to the identity map. So in other words, for every single kind of gamma less than alpha, F of gamma is equal to gamma. So this is kind of interesting. Not only, so if you take two distinct ordinals, they don't have the same, they have different orderings because there's not an order isomorphism between them. But also, there's no non-trivial automorphisms, order automorphisms of an ordinal into itself. In other words, like the only way to kind of well order kind of alpha, so you have the kind of same ordering, is to, like, if you start moving around the dots, you start actually changing what the ordering is of alpha. Or if you do move the dots and everything kind of stays the same, you haven't preserved the order relation at all. Okay. All right, so how do we prove this? What's the proof of this? Well, one thing to note is that it's actually just enough to show that f is the identity map. Because f is the identity map and our function is going to be onto, it's gonna follow that alpha is actually equal to beta. So note. So it's enough to show, well, that for every single gamma that's less than alpha, that, well, f of gamma is equal to gamma. And so how do we do this? What we want to do is just do it by induction. So assume, how does the induction work? Well, we assume that the statement's true for everything less than, say, gamma in this case. So assume for all theta less than gamma that f of theta is equal to theta. And our goal now is we want to prove that, well, our goal is to prove that, well, f of gamma is equal to gamma. And, well, how can we do this? Well, we can show that they're subsets of each other. So what's maybe one direction? We could say something like, well, if it's the case that, maybe we'll go with the backwards, we'll go from right to left first. So if it's the case, say, that theta is less than gamma, well, what can we say? We can say that we can apply the function to both of these pieces, right? Why? Well, theta is less than gamma, but they're both less than alpha, so they're both in the domain of our function f. So we can take f of both of these things. So f of theta is going to be less than f of gamma. But what do we know about f of theta? By our induction hypothesis, this thing is just equal to theta. So we have that theta is less than f of gamma. But that's what we wanted to show. Gamma, is going to be less than or equal to f of gamma. You could say it's a subset of, but we've proven already that, well, the subset relation is the same as kind of the less than or equal to relation for ordinals. Okay, well, what else do we need to show? Well, if we take some, and we'll use theta again, if we use some theta that's less than f of gamma, where our goal now is to show that, well, actually theta was less than gamma. And so how can we do this? Well, f of gamma, what do we know about f of gamma? F of gamma is less than beta, right? Well, then that means that theta is also less than beta. And so that theta is in the codomain of our order isomorphism. Well, order isomorphisms are onto. And, well, in particular, this implies, so if theta is less than f of gamma, then theta is less than beta. Great. Well, this implies that there's some maybe theta prime that's less than alpha, such that f of theta prime is equal to f of theta, right? F is onto, and, well, we have something in the codomain of our onto function, and so there must be something in the domain that maps to it. And, well, let's combine these two things together. Well, what can we say from both of these pieces? We can say that, well, so f of theta prime is less than f of gamma, right? Because, well, theta is less than f of gamma, and theta is equal to f of theta prime. Well, because f is an order isomorphism, what has to follow from this is that theta prime is less than gamma. Okay, that's just kind of doing the backwards direction of this kind of preserving truth part of the order isomorphism definition. Well, what can we say from this? Now we can use our induction hypothesis. What do we know? Well, we know that for every single theta less than gamma, that f of theta is equal to theta. Well, we have theta prime is less than gamma, so it must be that, well, f of theta prime, that's equal to theta prime. And so just combining everything together, what do we have? So from this piece, what we have is that, well, theta, well, actually from this piece, we know that theta is equal to f of theta prime. So that's from this. And then from this piece, we know that this is equal to theta. And then from the piece right before it, we know that this is less than gamma. But what did we just argue? Well, this is what we wanted to show. We just showed that if something is less than f of gamma, it's actually also just less than gamma. So it must then be that f of gamma is less than or equal to gamma, or that f of gamma is equal to gamma. Well, this is what we wanted to prove, right? This was the induction kind of step. And so the induction goes through. So that means that for every single ordinal less than alpha, it must be the case that, well, f of gamma is equal to gamma. And so then we get our result. So we get our result. So this is kind of more of a technical, I guess, lemma, but it's going to be useful for us in the proof of this kind of next theorem. Okay, so what is the result? This is kind of what we're going to prove in the next video. We can maybe list it as a theorem. And what we're going to be giving, so this is called maybe the Mostowski collapsing theorem. Sometimes I think I've seen it as a lemma, but this is called the Mostowski collapse. Mostowski collapse. And well, what does this result say? It's, well, if you have any well ordering, it's actually, it's order isomorphic to an ordinal. So that's one thing. But also the order isomorphism, the function that kind of witnesses that they're the same kind of ordering, that is unique. And I guess then the ordinal that that it's order isomorphic to is unique as well. Okay, so what's the result? So assume that A less than is a well ordering. Well, what's the result is that then there's a unique, so there exists a unique map. Maybe I'll write it first as an ordinal. So there's a unique ordinal alpha. And also there's a unique function pi from A into alpha, such that pi is an order isomorphism. So such that pi is an order isomorphism. Okay, so this is going to be the result. We'll give the more formal proof next time, but maybe just to think about some intuition as to why this might be true, or how could we think about. I always thought the definition of this. So maybe I'll also say that this pi. This is called the Mostowski collapse. So pi. The name for this function is called the Mostowski collapse. Mostowski collapse. So one way to think about this is with some examples. Like how do we kind of come to kind of construct such a function? The definition is normally a little bit strange, at least it was for me. One way to think about it is, let's say that we had something that was already well ordered, and one example would be, well, let's just take like, maybe we let A be the set. We'll think about it as maybe a subset of omega. Maybe we'll take like, 0, 2, 4, 5, 6, 7, and so on. So it's kind of all of the natural numbers except for we're getting rid of 1 and we're getting rid of 3. Maybe we'll get rid of 5 and 6 as well. Just, so maybe it'll be this. So 0, 2, 4, 7, 8, and it goes on like this. This is a well-ordered set, right? Because it's a subset of omega, and omega is a well-ordered set. And so by this result, there's going to be some ordinal that it's order isomorphic to. What is that ordinal going to be? It has to be omega. So what's going to happen here? So here's our example. We're kind of working with an example. Well, A is going to be order isomorphic to omega. Sometimes they write order isomorphism. You can write these like squiggly lines. Sometimes you also might see something like equals 2 with the kind of curly line on top. But I'll do the 2 squiggly lines for now, just to kind of save save additional strokes with the pen I'm using. Okay, so we know, and well, what's going to happen, right, is that, well, there's no like point at the end. These just go on forever. A should be order isomorphic to omega. Okay, so what we want to do is think about how we can construct a function from A to omega. And one way to think about this is, well, one thing that's going to happen is, well, we're going to take, maybe we'll list out A right here, and then kind of omega will do that over here. Well, the first thing is, well, the first element of A that should definitely map to the first element of omega, right? And then, well, the next element of A is 2. That should map to, well, the next element of omega, which is 1. And then, well, maybe we have 4 over here, which is going to map to 2. And then 7 is going to map to 3, the next element of omega. And it just keeps on going down like this. So it's maybe what you'd expect. So this would go on forever. Why is this called the collapsing lemma? Or why is it called the Mostowski collapse? Well, one thing to note is that, well, whatever our A value is, the value to the right, like the ordinal value that we're outputting, that's always going to be less than or equal to. So this right-hand column will always be less than or equal to the left-hand column. Okay, but one way to think maybe about what this right-hand side is doing is it's keeping track of the index of the stuff on the left-hand side, right? On one hand, we could have thought about listing out A as, you know, A0, A1, A2, A3, and so on. And, well, what this ordinal is doing is it's keeping track of what the index is. So this is our A0, this is what A1 is, this is what A2 is, A3, and so on. Okay. So, but what we'd like is, well, is there some description of what the output is going to be in terms of the previous stuff? And the observation for this is the following. Let's call this map, we'll call this thing pi. So this kind of map, so pi of 0 is 0, pi of 2 is 1, pi of 4 is 2, and so on. One way to think about this is, well, okay, this is just the empty set. Not very helpful at the moment. Well, what about 1? Well, 1 is the set 0, right? That's what the ordinal 1 is. Well, what is 0? 0 is what pi of 0 is, right? This is pi of 0. Or maybe I'll write it out like this. This is pi of A0. Right? Our very first element is A0. And then, well, we're doing pi of that gives us 0. And then that's another way to think about this. Okay, but maybe that's not helpful. What about the next one? Well, 2, that's the ordinal 0, 1. Well, what is 0? 0 is like pi of 0, or pi of A0. And then what is 1? Well, 1 is pi of A1. Right? Well, what is the output when we kind of input A1? The output after pi is going to be 1. Right? So 1 is pi of A1, and 0 is pi of A0. And so what's happening here is, well, this pi of A1, so what's kind of the conclusion from this first piece is that, well, pi of A1 is actually the set, well, of pi of A0. And then pi of A2 is really the set of pi of A0 and pi of A1. And then, well, pi of A0 is just the empty set. What's happening is, well, what is the output going to be? So what's going to be like pi of A sub 40? What is that going to be equal to? When we kind of go through this whole process, when we go through this whole process, what we're going to get is that this thing is going to be, well, pi of A0, comma, pi of A1, comma, pi of A2, comma, and then it's going to go all the way up to pi of A sub 39. So another way to think about this, and kind of if we want to write it out without the indices, if we have some element, maybe it's pi of A, what is its output going to be? Its output is going to be the set of all pi of B where B is less than A. So in this case, so A sub 2, right? Well, that was pi of A sub 2. Well, it's pi of A sub 0 and pi of A sub 1, the set of those two things. Well, this works for all of the values that we could pick. And one way to think about why that has to be true, kind of going off the definition, is that if there was some type of order isomorphism between A and omega, well, what would have to happen is that, well, A is an element, I'll do B is an element of A, or B is less than A, sorry. If and only if, I wrote B is less than B. B is less than A. If and only if, well, pi of B is an element of pi of A. And, well, one of the implications of this is that, well, pi of A, we can think of it as the set of all pi of B, such that B is less than A, right? If we can go maybe from here to here. Now, it's not exactly the case, right? If pi of b is an element of pi of a, all we know, I guess, is that, well, the set of pi of b's is a subset of pi of a. But if we kind of define pi, this function pi, the output to be exactly this equality. So pi of a, we define it to be the set of all pi of b such that b is less than a. Why are we going to be able to do this? Well, a is a well ordering, and so we can define things recursively on well orderings. So this definition is going to make sense by kind of our recursion theorem that we've proven before. This ends up working out, and this works out for all well orderings. So hopefully that made a little bit of sense. If not, you're welcome to kind of leave a question down in the comments or something. But I guess, so what this kind of Mostowski collapse is doing is we're kind of keeping track of the index of the elements, of our well-ordered set. So say that one more time. What this pi of a is doing is we're keeping track of the ordering of our, we're keeping track of the index of each element of our well-ordered set. Okay, so in the next video, what we'll do is we'll give a proof of this kind of Mostowski collapse theorem. And then what we're going to do from this is we're going to start working towards talking about cardinals. And probably, so right after this, we'll probably prove what's called Hartog's theorem. All right, so I'll see everyone in the next video.